I want to start with making a correction on the DFS procedure I described. So, I basically said look at the BFS algorithm and just use stack instead of queue. That's not quite correct. So, maybe I will again give a big picture of DFS because and then walk you through how on this graph where we started off, this graph, I said it uses stack and this is the tree, but let me tell you using the tree how using a stack how I would get this tree, okay, because I think there was a slight mistake in what I said. So, let me fix that first. Okay. So, DFS, so what BFS does is it starts at the vertex, puts all its neighbors in the queue, and then one by one it picks its picks the first vertex in the queue, puts all the white neighbors in the queue, and then it proceeds like that, right. So, and I said, oh, similarly DFS will do it on the stack. That's not quite right, okay. So, there is an initialization space, initialization phase where you initialize the queue to be, the stack to be empty, or put X there, and you initialize some time values, timestamps, because DFS uh, compute some timestamp, and the timestamp is useful, as I told you, for example, in computing the topological sort of a directed acyclic graph. So, there are various reasons to also store. The first time I visited a vertex, remember that number, last time I visited a vertex, that I explored its neighbors and went back. So, these are part of some initialization procedure, okay. And then after that, I said for every v in the neighborhood of x, this is what we called in the adjacency list, adjacency X. In BFS, we said just add it to the queue if it's white. Okay, if it's white. Here I am going to say no, just don't add it to the stack. You can add it to the stack. Right away explore DFS starting at that vertex recursively. So that's the difference. Okay, so let's just walk through that example graph I had. So 1, 2, 3, 4, 5 and 6. So, what I do is I add 1 to the stack, and I do not add all its neighbors into the stack like I did for Q. I add its first neighbor. In the for loop, it just goes there, and the first neighbor would be 2, and then I start exploring 2 before even I add other neighbors of 1. Okay. So, whenever I put it in the stack, it gets gray color. Okay. So, then I put it in 2, I am not even popping it out, I will pop it out only after exploring all its neighbors. So, I immediately explore its neighbor 3, because 2 has neighbors 3, 5 and 1, but 1 is gray. So, 3 and 5 are the white neighbors. Okay. So, initializations as the timestamp, stack, color, all that you do some initialization. Everybody is given white, things like that. So, the moment I start exploring DFS, first neighbor is 3, first white neighbor, or it could be 5, it does not matter. I put it in the stack. And then I go immediately explore 3's neighbors. 3 has 1, 2 and 4 as neighbors, 1 and 2 are already gray. So, I am going to put 4. Then I find out that 4 has no, so if you want to see the tree will look like this: 1, then I go 2, and then I go 3, and then I go 4, and then I find that 4 has no more neighbors. So, it is done, I remove it. and then I go to the top of the stack and see, have I explored all the neighbors of 3? No, remember it is inside that for loop. For every neighbor, white neighbor of 3, you do something. So, I pick the first neighbor which is 4 and explored it. Now, I have the for loop will come to the next neighbor which is 5. So, I will add 5 to the stack, because that is the white neighbor which is a neighbor of 3. So, in other words, I am exploring that 5. And then I explore 5's neighbor before I even finish 3. I do not know whether I finished 3 or not. So, I will explore 5's neighbor which is 6. So, I will explore that 6, and 6 has no more neighbors, gone. 5 has no more neighbors, because 5's neighbors are 2, 3 and 6. 6 has already become gray, black and all that, and 2 and 3 were already gray. So, no more neighbors, so it is gone. And then it comes to 3, no more neighbors, and then I come to 2, no more neighbors, 1, and stack is empty. Okay. So, DFS tree will look like this, and this is slightly different from the tree I drew before, but there are many DFS trees, because the order in which you visit the neighbors can change, and that would change the tree. But this is the DFS tree and this is the change. Okay. So, it is not, unlike Q, we do not throw all the neighbors into the stack at one shot. The moment you put the first neighbor, you explore that, because you are going deeper. So, that is a difference, but everything else what I said is fine, that it is, if you analyze the running time, it is one outer loop which just goes through all the vertices, and then you are looking at the neighbors of a vertex. So, it is again because of the recursion, there is slight complication in the analysis, but still you can verify that it takes order m plus n time if you use adjacency list. If you use adjacency matrix, it is n square. Okay. So, that is the end of BFS, DFS and some applications I mentioned about it. Now, I will briefly talk about algorithms on weighted graphs. Which means your graph, apart from V and E, there is a weight on the edges, let us say some integers, positive integers, natural numbers. Okay. Could be real numbers, you could have negative numbers, but for our purpose, let us stick to positive numbers on the weights, and these weights refer to cost or distance depending on your application. So, here again now the interesting questions are single source shortest path. Is one of the interesting algorithmic questions. I want to start at some vertex x and find distances to every other vertex. Now, when you say distance, it is not just the number of edges in that path, it is the sum of the weights on the path, on the edges in the path. Okay. So, this is what makes it different from BFS. If all weights are 1 or the same, then you might as well apply BFS, it will give you shortest path from x to every other vertex. But the distances vary, then BFS does not give you the shortest path. You can come up with very simple example. I might have a path which is to from S to T, ST edge, there is only one edge. If you count the number of edges, it is 1, but the distance is 10, whereas if you go through A, even though it has 2 edges, the distance is 8, which is smaller than 10. So, that is a problem, and there is a very classic algorithm due to Dijkstra which sort of mimics BFS, but takes into account that there are edges have weights, and so it does something little more. Rather than using a queue, it uses what is called a priority queue. Okay, so let me briefly describe how it works. So again, we are going to grow something like BFS starting at some vertex. Let's say S is that vertex. Then I am going to create some S, and then the remaining vertex is V minus S. The S initially is small s, and V minus S as every other vertex. Okay, and what BFS does is it starts from a vertex and picks the nearest vertices from that vertex, where the nearest is the based on the number of edges. So that means it picks all the neighbors first in the case of BFS. Here we want to pick the nearest in terms of the distance. So first thing what we will do is, for every vertex we will remember a distance, which is length of the shortest path from X through vertices in S. Okay. Somehow S is this set of vertices for which I already know shortest paths from S. So this is sort of like dynamic programming and greedy mixed in some sense, okay, depending on how you think about it. So I want to find the shortest path from S to every other vertex. So one by one I am going to gradually find shortest path from S to some small, initially a few vertices, and those vertices form the set S. Initially that S contains small s, because I know shortest path from S to S, the small s to small s, its distance is 0. Okay. For every other vertex I am going to remember, somehow pre-calculate and store length of the shortest path from X to that vertex, S to that vertex. But the intermediate vertices all belong to capital S only. Okay. So the shortest path can go like this and then come back to X. It cannot use vertices of V minus S. Such paths I am going to find the shortest distance and store them, pre-compute. So initially, quickly think about and tell me what is initially what it is basically dV for V in V minus S is minimum of the weight of S comma V and infinity. So if there is a direct, because capital S only has small s and I am allowing paths only through vertices in capital S. So if there is a direct edge, I will use that weight of that edge in dV. If there is no edge, I will put infinity. Okay, so the every vertex here has a distance stored. Now algorithm, Dijkstra's algorithm find and delete the vertex in V minus S with smallest d value. That means among vertices here, find the one which is the smallest d value and delete it from V minus S, include it in S. So let's call that vertex as some V, right? So that means S, it becomes S union V. Now update the distances. Remember, the definition of dx is length of the shortest path from S to X through vertices in S. So I had stored initially, but now that I have added one vertex into capital S, the distances for some vertices in V minus X, the shortest path distance, may change now because I have added V into S, because it is all through vertices of capital S, right. So I had my S and I had stored my D values. Now my S got some other vertex V, so D values, some of them may change, because earlier there was a shortest path from S to that vertex, but maybe through V the shortest path may be smaller. Okay. So it's not very hard to notice that only neighbors of V, we just need to check. So let's call X as a neighbor of V, D of X equal to D of X plus weight of XV, or maybe there was a path. So take the min of these two. That is, earlier there was this D of V stored, let's call D of X, through some path, but now through V there may be another path. That distance will be D of X plus weight of XV. This is, yeah. So see, whichever is smaller, whatever you had stored before or the new one, whichever is smaller, update the D values. That's it. Now what do you do? Repeat. Now you have new D values, find the smallest D value, include it into S, update the neighbors of the whatever you included by doing this min computation. Find the smallest, add it, and so on and so forth. At the end of it, capital S, the D values initially, I am also going to say ds is 0, obviously, right. At the end, dv for all v in S is the length of the shortest path. Now, it's sort of like dynamic programming. I am only storing the distances, but if I actually need the path itself, then you need some more bookkeeping, right? Use some sort of a parent information, whichever is, whenever I find this min happens to be due to X, then you know the shortest path to X goes through V, due to V, which I added. So X its predecessor is V, just remember this now, right. Otherwise, whatever was the predecessor will be the predecessor. Okay. So you need some more bookkeeping to actually compute the path, but this code actually computes the distances. Okay. So I am going to say, remember predecessors for every node, because to start with you are only keeping the neighbors of S some distances, the predecessor will be S, but through some other vertex, if the path is smaller, then you will change the predecessor to that some other vertex, right. Remember the predecessor vertices, remember and update to actually compute the shortest path. Now some remarks, important remarks. Okay, works only if edge weights are non-negative. In particular, if you have a negative weight, then you can actually see some examples where Dijkstra's algorithm may not give you shortest paths. Okay, this is important. Why correct? At the end, when the algorithm stops, why does it give you the length of the shortest paths? It requires proof. Okay, you can verify, but as we have been saying on dynamic programming and greedy algorithms, any optimization algorithm, once you've solved it, you have an algorithm, you have to argue why it is correct. The book, Carmen's book, actually has a proof of correctness. Even if you don't do the proof of correctness, at least emphasize that it requires a proof. It's not enough to run an example on Dijkstra's algorithm and say this is Dijkstra's algorithm. At least make sure students understand that there is a requirement for a proof of correctness of Dijkstra's algorithm, and it works only when the edge weights are non-negative. If you have and the proof critically uses the proof of correctness uses the fact that the edge weights are non-negative. If there are negative edge weights, Dijkstra's algorithm fails. But here is a important thing which I believe you can do. How much time does it take? Okay, so the algorithm is essentially this loop. You have some distance. So there is this pre-computation or initialization, and then in the loop you are deleting the smallest element from some number, some set of numbers, and then updating some values, deleting the smallest, updating some values, delete min, delete min, delete min you are doing, and then updating change values. Okay, this is what you are doing. So what would be a good data structure to use? Think about it, right? Heap, right? So please work out. I will maybe set it up in an example, in an exercise, that with and without heaps. How much time does it take? Order what? Please go and implement. I mean, I know you ask students to implement, you may have even implemented it, but do a quick running time analysis also. And you have a bunch, basically you have an initialization, a bunch of numbers, you are removing the smallest and then updating the neighbors of that vertex, the values, removing the smallest, you are doing again and again. What would be the cost of a naive implementation? What would be the cost if you actually use heaps? Please check. Again, here is an application of heap. Very nice, clever application of heaps. In the context of shortest paths, there is this all pair shortest paths. There are a lot of, you can, if edge weights are non-negative, remember, Dijkstra's algorithm finds the shortest path and the lengths from a source vertex. Now, if I want shortest paths between every pair of vertices, all you have to do is to try every vertex as a source n times. Okay, so n Dijkstra is one algorithm if the edge weights are non-negative, because Dijkstra's can be applied only if the edge weights are non-negative, and otherwise there are dynamic programming algorithms. This is again a a right appropriate example for dynamic programming implementation, because you have what is called as optimum substructure property. Because if you have a shortest path from S to a vertex T, then for any intermediate vertex, what you have is actually shortest path from S to that vertex, because otherwise if you have a shorter path, you could have taken that to even go to T also. So this is the cut and paste argument. So there is a natural dynamic programming algorithm, so you can come up with some subproblem, make some choices, right? I'll tell you the kind of choices you use. Dynamic programming, I have told you, you make some choice that tells you what are the sub problems, and then once you fix the sub problems, what is the order in which you compute the sub problems, and start computing bottom up. So here, for example, the choices you make on the length of the paths. You can say I want to compute the shortest path from from I to j using at most one edge, using at most two edges, using at most three edges. You can build your solution that way. Okay, so that's what length of the path, or on the intermediate vertices. Right? You can say I want to find the shortest path between I and j for every I and j. That's what it means by all pairs, where I am allowed only some 1 to k as intermediate vertices. Okay, maybe empty set as intermediate vertices, then you can only look for edges. Then you gradually include, I suppose I include 1 as intermediate vertex, 2 as intermediate vertex, 3 as 1, 2, 3 as intermediate vertices, and gradually expand. And that's a choice function you can use, and then break it up into sub problems and do. Okay, so now since all of you have done dynamic programming, this is a good example to try how you would do in dynamic programming algorithm for all pair shortest paths. Please check the books and verify the running time and see how it is better than maybe trying all source, running your shortest path from every source. Of course, if the edge weights are non-negative only, you can even try that. Okay. And of course, if the edge, there are no weights on the edges, then you have this BFS, try from every vertex kind of a solution. Intermediate set of vertices. Okay, so this is one class of problems we are interested in on weighted graphs, which basically shortest paths, single source, all pairs. The other problem, again I'm going to mention, give a very brief overview, is the minimum spanning tree problem. So here again you are given an undirected graph with weights on the edges. Right. Imagine that the weight on the edge is the cost of, assume it's a road network, and the weight on the edge is the cost of relaying the road. The road has become bad, you want to relay the road. So now, what is your goal? Goal is to find a subgraph find a connected subgraph with minimum total weight. That's the problem. Right? Imagine I want to relay some of the subgraphs. So that means some of the roads. I want to relay some of the roads. So those edges will form my subgraph, and I want it to be connected, because between every pair of intersections I want a good relayed nice path, and I want to minimize my total cost. Okay. So, one immediate observation is that such a subgraph must be a tree. There is no point in having a cycle in such a subgraph, because if all I want is a connected, if I remove one edge from that cycle, it will remain connected and the weight will come down. So, since I am looking for a minimum total weight, it's a minimum tree, and it's called spanning, means it contains all vertices. So, there are essentially two common algorithms for minimum spanning tree. You would have seen both are greedy algorithms. One is due to prim, which really works more like Dijkstra's shortest paths algorithm. Okay. So, at any point of time, again I have an S and B minus S, and S contains some starting point, some arbitrary starting point. So, the algorithm goes like this, Prim's algorithm. So, S is small s, find a minimum weight edge between S and B minus S. So, among all edges here, I pick the one which is the smallest weight, I include it. Okay. So, let that edge be u comma v. Then I am going to add S is S union V. So, that means this vertex is now added to capital S. Repeat, that is it. Again, the new minimum weight edge after I add V is the next minimum weight edge, which suppose I had kept it in some sorted order on the edges or something, or look at V's neighbors now, right. These are new edges coming into this what is called a cut. I need to look at those edges along with whatever edges before and find the minimum weight edge and keep adding it. This is it. This is Prim's algorithm, and you need to argue correctness. That at the end, I mean, repeat until what? Until V minus S is empty. That so you would have every time you are adding an edge and a vertex into capital S will have this big spanning tree. You need to argue correctness and you need to argue implementation. Here implementation is again using heaps. Please go and check with and without heaps. Maybe if there is time, I will talk about it in the open session. Because you really need to store the edges in some sort of a heap, the edge weights, edges across S and B minus S. You throw away the smallest weight, that's like a delete min, and then you are adding some more edges to your set. So, like an insert and delete min. Okay, so that's the kind of thing you will do. So, heap is a very nice data structure to do it. It has a very similar flavor as Dijkstra's shortest path. Okay, why does it give you a correct algorithm at the end? It requires a proof, but algorithm is very simple. I have actually essentially given you the entire algorithm in English. You can convert it into a program. There is another algorithm due to Kruskal, which goes like this. Step 1, arrange edges in non-decreasing order of the weight. So, it is also greedy. In some sense, you are trying to pick a subset of edges so that the remaining subgraph remains connected and is of total minimum weight. So, I am going to take the smallest weight edge. So, let us say, so let us call these edges E1, E2 up to EM. Now, step 2 is essentially a loop for and start with an empty subset of edges for I going from 1 to M. If F union EI does not have a cycle, then I am going to add EI. That is it. Okay. So, let us look at this example maybe. What would Prim do on this algorithm? What would Prim do on this example? So let us say I start with B and everything else outside. So, it will pick the smallest weight edge out of B. So, it is going to pick that edge 6. Then BE on the one side and everything else on the other side, and then it is going to look at the smallest weight edge from this BE side to everything else. You can verify that it is actually BA with the weight 7. Then with BEA on one side and everything else on the outside, what is the smallest weight edge it is going to pick? It is going to pick BC, which is of weight 15. So, then ABEC on the one side and D on the other side. What is the smallest? DC would be 21. So, it is going to pick that, and this would be the subset of edges it is going to pick, whose total cost is 13, 28, 49, and it is connected. It has all the vertices A, B, C, D, E. This is what Prim's algorithm will incrementally compute this subgraph. Well, let us see what Kruskal will do. It will take the smallest weight edge and add it, which is BE, and make it 6. Then it will pick the next smallest weight edge, which is BA, with weight of 7. Then it will look at the next smallest weight edge, which is EA with weight 9, and then it will realize that it forms a cycle with whatever I have picked. So, I am going to ignore it, because the algorithm says if it does not have a cycle, then I am whatever I have picked plus this edge does not have a cycle, then include it. Whereas now 9 forms a cycle, so ignore it. Next edge, cheapest edge is BC with cost 15. So, I will add BC, and then the next cheapest edge is 21 CD. Same tree it produces with a total cost of 49. Okay. So, they are inherently different algorithms. One sort of grows at any point of time it maintains a tree, and moment it reaches every vertex it stops. The other algorithm maintains a forest, not a tree, collection of trees, and just picks the next smallest weightage, smallest weightage, smallest weightage, as long as it's not forming a cycle, and it stops when everybody gets into one component. So again, important to talk about correctness because it's an optimization problem. Why does it give you correct algorithm? Remember, it's a greedy algorithm, and I said typically greedy algorithms require a proof of correctness. So at least impress upon the fact that you need proof of correctness, even if you don't do proof of correctness. Okay, Carmen's book actually has a correctness argument, and implementation uses with and without disjoint set union data structure. I mentioned when I talked about this data structure that this actually was developed for implementing this algorithm, because at any point of time, what do you have in CRISPR's algorithm? You have a collection of components, connected components, or a set of vertices forming a connected component, a family of sets. Right. Initially, I started, every vertex is a singleton. The moment I add B and E get connected to one component. Then I add A got connected to one component, and so I am doing unions. Find whether the endpoints are in different components. That's what this means. That how do I check whether the end? This means that endpoints of EI are in different components of F. And that we know how to compute using the union disjoint set union find data structure, where you maintain these sets in some form. I remember I mentioned an array, and you do whenever they are in different components, you do a union. If they are in different same component, don't include that age. Finally, the answer F is the final answer. Okay, so that was a very quick refresher on graph algorithms. Two fundamental graph exploration techniques, BFS and DFS, both take order m plus n time, and one uses an array a queue to implement it, another uses a stack to implement it, because it's a recursive algorithm. And each one has interesting different applications. You can check for whether the graph is connected, bipartite, find all connected components. You can find cut vertices, you can find strongly connected components in directed graphs, you can find topological sort of a directed graph, and so on and so forth, using these exploratory procedures. That was one set of algorithms we saw. And then on weighted graphs, you have shortest paths, single source, all pairs, edge weights being non-negative or even negative edge weights allowed. Famous algorithm, Dijkstra's algorithm, there is Bellman-Ford, Floyd, Warshall. These are all for all pair shortest paths, the two dynamic programming algorithms. And then we saw minimum spanning tree algorithms, famous algorithms by Prims and Kruskal. So together what I did in these two lectures would form a good review of fundamental and basic graph algorithms. Two other important points. Correctness of these algorithms are important. You need to argue, at least impress the fact that proof is required. And second point, implementation using efficient data structures. In all these algorithms, we saw powerful use of data structures, stack, queue, heap, and disjoint set union for different set of algorithms. So, I mentioned already when we talked about data structures that there are two applications. One is that, like in Google or in databases, just supporting queries efficiently is the requirement, that is the application. And there are times like in algorithms, you want repetitive steps which you can be efficiently implemented using better data structures. Okay. So, hopefully with this you have a good picture of some basic graph algorithms. Again, each one, to do it in detail with example, implementation, correctness, would require 1 or 2 lectures for each of these algorithms. I have sort of compressed them in about 2 hours, because my goal is just sort of give you a high level overview. With this, I will now complete graph algorithms, and in the next week we will get to the last week of this lecture on the theory of NP completeness. Thank you.